Today I'd like to talk about the basics of alternating current or AC circuits. Describe a little about how we describe those kind of waves that'll set us up for what we want to do in the future. First, let's set the overall picture. What we've done so far is we've talked about time-independent solutions or DC circuits. The values don't change with time, so we set something up and then that's what the value is as a function of time. What we want to move and talk about is, that's only so interesting, we want to move and talk about time-dependent solutions, right? And there's essentially two parts. We talked earlier about transients, right? That's where we put R and C with a DC power supply. There's some transition from when I close the switch to when it reaches its steady state. So that's where sort of in transition to DC, right? Because really that closing the switch is really sort of a time-dependent solution. But that's not our main concern. So that exists. But what our main concern is sort of what we call AC circuits, where we change the voltage in some regular steady state way. So we can reach a steady state solution, right? One that's sort of consistent over time, but all the potentials and the currents all change with time, just in some regular way. So first, let's think about a battery hooked up with two resistors, so voltage divider, and we know how to plot the potentials, we can figure out the current, we can figure all this out, and you could imagine dialing down the current, the power, the battery, the power supply, turning it lower, reversing the polarity of the battery, and turning it up even more, right? So we could do each one of these solutions. We know how to do that. And so really AC is a matter of changing the voltage of the power supply in some regular way. And so if we do that, you can see here, we're just going to change the voltage. And so you can see the current alternating. First we're clockwise, then we're counterclockwise. So that's sort of where we get the name from, alternating current. But essentially at any given instant of time, it's still a DC case. It's just the next instant of time. The potential of the battery or the power supply will be different. Okay, so how are we going to describe these waves? Essentially, these are the four types that you're most likely to see, sort of a sine wave, a square wave, a triangular wave, or a sawtooth wave. So these are on the signal generator. These are options that you'll have. But the main point is they all repeat regularly. So this is what the steady state solution is. That's going to be a consistent over time. So usually we use sinusoidal. That's the most common, where we represent the voltage or the current as some maximum value, V peak. That's representing the maximum value times some sinusoidal function. The period is the time to complete one oscillation. It's the time for the wave to repeat itself. That's inversely related to the frequency, which is the number of oscillations per time. So in this problem right here, or this example right here, you can see this wave. It does one wave or one oscillation in 8 seconds. Okay, so the frequency would be 1 in 8 seconds. Now if we had a different wave, one with a smaller period, we get something like this. Here the period is 4 seconds, so we get 2 waves in that 8 seconds, or it has twice the frequency. We get twice the number of waves per second. So in the lab we usually talk about period and frequency. But when we sort of describe waves using theory or using equations up here, we use the angular frequency, which is really just not the number of oscillations per unit of time, but the number of rotations per unit time, or the number of radians per second. Okay, and so this right here is the schematic for a AC signal generator. Now it could be a sine wave, square wave, triangular wave, or a sawtooth wave. So now let's look at a voltage versus time graph. So right here, this would be our signal generator, and this graph right here would be the output of that signal generator. It has a period of 12 seconds, frequency of 0.167 hertz. V peak is 10 volts. Okay, so this is how we describe the wave, or what we'd see on an oscilloscope if we measured it. Well, let's look at 3 particular points. We can look at time t equals 1 second. At this point, the voltage of the signal generator is 5 volts, right? That's just like our DC problem where we had a 5-volt battery. We know how to do that. We can figure out the currents, we can figure out the potentials, the potential differences, and we can figure that out. So that's that time. We can do time equals 6 seconds. This is when the voltage across the leads of the power supply are 0. Okay, and so we know how to do that problem. And the next time is t equals 9 seconds when the voltage across the battery is minus 10 volts. Okay, so we know how to do that. Now sometimes when we draw these pictures, we also could plot, right? We can read off these graphs. We could also plot what's the potential across resistor 1 and the potential across resistor 2 as a function of time. And those are also going to be sinusoidal. And it turns out that if you add V1 plus V2, that should add up to the voltage of the signal generator, right? So that Kirchhoff's loop rule is satisfied. Now the way I've plotted these here, I've sort of plotted them where I'm plotting the absolute value of the voltage across the two resistors. And so we know the voltage of the signal generator is positive. The voltage across R1 is negative, R2 is negative. So I can rewrite them in the following way. And so what I'm really plotting isn't what's the change in potential across each of the elements, but what's the absolute value. So when we talk about characterizing AC signals, typically the easiest thing to do when you want to characterize something is just talk about the average value. But the problem with sort of sinusoidal functions is the average value is 0. So that's not very helpful. We know things are changing, but the average value isn't telling us what that change is. So instead we use the root mean square, which is essentially the average of V squared. And so we essentially square the value, take the average, take the square root. And so for a sine wave, if you do all of that mathematics, you get that VRMS, the root mean square voltage, is just 0.707 times the peak voltage. And so that function can vary, right? For a sine wave, it's always 0.707. For a triangular wave, it's 0.577. And you can calculate it for whatever you want. But every sine wave, independent of the frequency or all that, is always going to be 0.707. So if you know the RMS, you know the peak. You know the peak, you know the RMS. And just in general, uppercase typically indicates a quantity that doesn't depend on time. The peak-to-peak voltage, the peak voltage, VRMS, those are things that don't vary with time. And the lowercase indicates that it does depend on time, the voltage at any given time or the current, those kind of things.